Can someone sum up what we covered so far? Chapter 11. You know, go for it.
Bohr theory, or
Well, even before Bohr theory, you know, the whole start of it.
Back to atomic theory.
Yeah, atomic theory's what we're into, but
quantum mechanics.
quantum mechanics, that's true. That's where we ended up at, pretty much, is quantum mechanics. But how did we get there to quantum mechanics?
Light.
Light. That's right, light. What about light? Uh-huh.
Passes through
Yeah, electrons and light interact, that's for sure. But before that, though,
Like gamma rays and X-rays and stuff.
yeah, the electromagnetic spectrum. Talked about that. You should know, like gamma ray, X-ray. What does it go? Gamma ray's highest energy, then X-ray, ultraviolet, violet. Yeah, the Roy G. Biv thing. Infrared. Microwave. You should know those. And so what about the light?
All light goes the same speed.
All light goes the same speed?
It's just different frequency.
Yeah, different frequency and different wavelengths and different frequency, different wavelength, and different. One more thing is really important. Frequency, wavelength, and if it's high frequency, then we say it's short wavelength, and high frequency is high energy. Yeah, high frequency is high energy. So it's you know, light. Light has different frequencies, different wavelengths, different energies. So what about light? Okay, after light, then we looked at what? No. Uh-huh.
Didn't we say like that was a way for particles?
Yeah, light acts as a wave and a particle, but that came later on. Before that, we said something else. This is kind of what you want to do, you know, if we're studying, just summarize the whole thing. Then it would just develop, you know. Let me tell you, I was looking for spectroscopy next, and then et cetera, et cetera. Eventually, we got to the end. The end is the quantum mechanics, and so there's not that much of the quantum. There is some quantum in your book, but it's not enough. And so this is a supplemental section on quantum. Actually, quantum numbers. Where did quantum numbers come from? we got the quantum, we got this other stuff, and basically, this goes into it much more depth than their book. The book's figures aren't so great. And so if we go to quantum 1 through 11, take a look. Here's quantum 1, page 1. Quantum numbers, electronic structure, and we went through this stuff here, and then we generated the diagrams here. Some pictures of this. Something like this. There's a whole bunch of diagrams here. This one's good. This one. So what you should do is you should go through and just be able to describe the whole story in your own words. We end up with something like this, and then what was this diagram called again? Yeah, orbital energy level diagram. Or energy level diagram, or later on we'll see, you'll see there are atomic orbitals and molecular orbitals. We're just looking at the atomic orbitals. So this is also called an atomic orbital energy level diagram. But we have here is the 1s. So go ahead, rather than call it 1, 0, 0. 1s is in the first shell, and then 2s in the 2p, the next shell. What's the next shell after that? 3s. And then the 3p. How far should you know this? That would be in the third shell. But one set of orbitals that doesn't occur in the third shell is what? The 3D. The 3D actually go into the fourth shell. You can see it there. It's a little more space. You can see it a little better. The 4s. Fourth shell goes 4s, and then the 3D. There are 5 of those. 3D, and then the 4P. The 4D actually end up in the next shell, which is the 5th shell. And so those are the shells. Here we could see more of a breakdown of these. First shell, second shell, third shell, fourth shell. These are called the principal energy levels, where n equals 5, and n equals 5 there are 25 individual orbitals. Do you know how many subshells are there? N equals 5. How many subshells do you expect? Close. Just count them. There's the S subshell, the P subshell, the D, you're right, D subshell, and the F subshell, which is 4. Right. Do you see a pattern? Well, there's something missing out of this. You don't really see the pattern here, but you'd see the pattern if you looked at the entire thing. This one is cut off. This one's cut off because they base it on the ground states for the elements in the periodic table. But actually there are more orbitals here. So for example, they just show 7s and 7p. Is that all? So, the pattern's a little bit tricky to see. So when n equals 1, how many subshells are there? 1. When n equals 2, how many subshells are there? N equals 3 has 3 subshells. N equals 4 has 4 subshells. N equals 5, they're missing a subshell. Do you know what subshell they're missing out of here? When n equals 5, they're missing the G subshell, because the G subshell is up in the next higher. Actually, the next higher. Maybe it's the next higher. We got to look at how it's factored. So there are 5 subshells actually, and so it goes like this. You know, for every n, there are going to be n subshells and n squared orbitals. Those are things we can notice if we map out the entire thing, but we didn't map out the entire thing here. These are the subshells of the sublevels they have here, the S, the P, the E, the F. Just separating them horizontally to keep better track of them. All right, so we can go ahead and use some quantum mechanics now. So let's look at the carbon. Look at carbon. How many electrons does carbon have altogether? So based on the periodic table, we go with C. It has a total of 6 electrons here. So for those 6 electrons, how would we fill those in? And so we go to the 1s and we use the rules for filling in the orbitals with electrons, so 2 electrons max. So we take care of the 1s. So when we do the 1s here, that completely fills the first shell. It just takes 2 electrons to fill it. So we're going to look at, this is quantum. Quantum should describe, be a fundamental description of chemistry. If we look at the periodic table here was kind of organized based on observations. The periodic table predates quantum mechanics, so this is the general organization. But the way it's organized is by shells here. So the first shell is going to contain 2 electrons. So that would be the first row here. First electron would be like hydrogen. The second electron would be like helium. So this first shell, if we fill that, then we're like helium up to here. And we put these square brackets around here to say that this is like helium. But we have more than 2 electrons, so we're going to go past that. 3 electrons would be like lithium, 4 electrons beryllium. That would fill the 2s subshell or sublevel. And then we have to move on to the 2p. So how does the 2p fill? So I have the 1 electron there. I have 1 more electron. So I have 2, 4, 5. Where does my 6th electron go? Should I pair it or do I pair it? No. Let's spin it to the next one. It has to be parallel spin. So this would be carbon as a partially filled second shell. A partially filled second shell, well, turns out there's some stability to a filled shell. So in order for carbon to fill this second shell, how many electrons would they have to gain? They'd have to gain, let's see, actually we could go over here, 1, 2, 3, 4 electrons. And so that means carbon could potentially gain 4 electrons, giving it a -4 charge. Or carbon can just alternatively lose how many electrons? 2. Well, maximum. Not 2. What's the max carbon can lose? 4. So if it gains 4, then it's going to fill the second shell. If it fills the second shell, then it's going to be similar to, well, if we fill the second shell, we're going to be similar to neon. So you go all the way up here, you get neon. Excuse me, neon's pretty stable, helium's pretty stable. And so that's a filled shell there. If we lose these 4 electrons, then we'll be like helium. And so nothing happens with these, the 1s electrons. So what we say is this. We say that the outer shell electron is where the chemistry happens. The outer shell is termed the valence shell. So if we want to understand the chemistry of carbon, we look at the valence shell. Carbon would like to gain 4 or lose up to 4 electrons based on the shells here. So filling these shells is important for having a filled shell. And so the first shell is helium. The second shell, if we fill that completely, we're at neon. Do you know where we're at if we go and do the third shell? Argon. And then the fourth shell, if we completely fill that, we'd be at krypton. When we look at it, this is how we're filling it. Each element is 1 additional electron. And so an s orbital here, this would be the s orbital, would hold 2 electrons. The p orbital, we have 3 p orbitals. Each p orbital holds 2 electrons, and that's a total of 6 electrons. And so carbon has 2 p electrons, nitrogen 3, oxygen 4, fluorine 5, and then neon 6. So there's completely filled p sublevel here. Neon. These electrons here don't really participate in chemical reactions. These are called core electrons. Core shell, or shells. There could be more than 1. In this case, it's only 1 shell. Excuse me. Core. And so, let's take a look at some others here. Before we do that, this is the most descriptive, and we could keep drawing the empty orbitals up here, but this is called the orbital energy level diagram. Energy level diagram. The problem is orbital energy level diagrams take up a lot of space, and it's not the most compact way of doing it. And so what we can do is we can sacrifice a little bit of information and come up with another type of diagram, which is called an orbital box diagram. In an orbital box diagram, for carbon, we would have a 1s, and would be represented by a box like this with 2 arrows inside, opposing each arrow representing an electron. And then after the 1s, we're going to have 2s, and then 3 2p's that are drawn like this. I mean, 2p orbitals with 2 electrons in them. So this would be an orbital box. In an orbital box diagram, what information do we lose? What information we lose is a little bit about the relative energy. For example, here, it's hard to show there's a big jump between 1s and 2s and a small jump between 2s and 2p in terms of energy. Orbital boxes are just evenly spaced out. These 3 orbitals are the same energy. That's why they form one big block versus some of the others. So that's the orbital box diagram. But what's even more compact is something called the electron configuration. Electron configuration, we lose additional information. We lose information about the spin. But what we do get back is a little bit of space savings. And so this is read 1s, not squared, but 1s2. That's to indicate that there are 2 electrons in the 1s orbital. And then we have the 2s orbital next, and then we'll indicate the number of electrons as a superscript, so this would be a 2s2. And then we have the 2p orbitals next. The 2p orbitals have a total of 2 electrons. The maximum capacity of the p's is 6 electrons, so it's a partially filled 2p sublevel or subshell. So we lose the spin information, and so the most informative are going to be the electron, the energy level diagrams shown. The electron configurations like this, although we could get more detailed, for example, 1s2, 2s2, and then we can split up the p's. You know, if you recall, there's a 2px, we'll put 1 electron there, and a 2py, 1 electron there. 2pz is empty in this case. Just going by convention. That's another way of representing. Another way of representing this is to show the helium. Use this symbol as an abbreviation for 1s2. Helium is 1s2, and then we'll write 2s2, 2p2. This shows the core electrons here and the valence electrons. A little easier to see. There's carbon. If we go to silicon, silicon's right below carbon. Silicon is 14 electrons. Okay, so 1s2, this 2s, 2p with 6 electrons, 1, 2, 3, then pair 4, 5, 6, and then 3s2 with 2 here, and then 3p, 3p, actually probably can't see it. Let's do this. How am I reading those off? This is how I'm reading those off. I'm reading those off because I know this, the theoretical basis for the periodic table. Again, Mendeleev started organizing the periodic table well before quantum mechanics ever came to be. But, this is how I'm reading it off. So we have the first shell, the 1s, all the way to helium. We have the second shell, the 2s, 2p, all the way to neon. Third shell, 3s, and the 3p to argon. The fourth shell is going to be 4s, 3e, 4p. The fifth shell is going to be 5s, 4d, 5p. Sixth shell is going to be 6s, 4f, 5d, 6p. Goes like that. We'll talk more about that as we go on. And so when we look at this, we're filling the first 2 shells. If we fill the first 2 shells, then that would be equivalent to neon here. And so what we end up with is this, as far as electron configuration goes. This would be the most compact way of representing it. It'd be neon 3s2, 3p2. So if we look at the electron configuration for carbon here and compare it to the electron configuration for silicon, we see, you know, the core be a neon core rather than the helium core, and the valence electrons here be like this. But, you know, silicon, what do you think? Silicon can gain how many or lose how many electrons? In order to fill the third shell, how many electrons does silicon still need? 4. Or it could lose the third shell entirely and be left with just the neon core. If it loses the third shell entirely, how many electrons would they have to lose? 4. And so this is silicon and carbon that's very similar. The charge or the oxidation state ranges from +4 to -4. And in fact, we call this the valence shell electron configuration. If you look at the valence shell electron configuration for carbon, it's 2s2, 2p2. The valence electron configuration for silicon is 3s2, 3p2. And so it's the same. The only difference is the n. And so what we call this is we call this the ns2, np2 electron configuration, or we just change n. And in fact, that forms an entire family. And so let's take a look at this family here. So here's carbon. They didn't use helium here for the core. We have the helium and then 2s2, 2p2. It doesn't take much time to write 1s2. Here, they did write the neon core, so it's 3s2, 3p2. So these are members of the same family. They can gain up to 4, they can lose up to 4 electrons. So it's the same. We see this here. If we look at boron, it's 2s2, 2p1. Aluminum, 3s2, 3p1. Same valence shell electron type configuration, although the n is different here. But what happens here? Take a look. Carbon goes to silicon, goes to germanium. Germanium appears to be different because if you look at germanium, how many valence electrons does germanium have? So germanium, well, let's look at how many total electrons germanium has. Germanium is going to have a total of 32 electrons. And so if we start off with 1s orbital here, we'll have 2 electrons there, and then the 2s orbital, 2 electrons. 3 2p orbitals with 6 electrons. That takes me to 10 electrons of neon. Then we go to 3s, 2 electrons. And then 3p with 6 electrons. Is that right? Yeah. P with 6 electrons. It takes me to argon, and then from argon I'll go 4s with 2 electrons. And then the 3d, how many electrons have I used so far? Argon's 18 electrons. So 2 electrons for helium, 10 electrons total for neon, 18 electrons total for argon. And so that's 18, 19, 20. Let's hit the d orbitals. This will be the 3 ds. 21, 22, 23, 24, 25. It's Hund's rule. 26, 27, 28, 29, 30. That takes care of 30 electrons, and then I have 2 electrons left over. Those must go into the 4p, according to Hund's rule. Like this. Now, a funny thing happens because you'd think the core electrons would be argon here, argon. But the 3d electrons are different. You know, even though these 3d electrons are, what shell are those in? The 3D electrons, are those in the third shell or the fourth shell? They're in the fourth shell. But a funny thing happens with these 3D electrons, and that is this. Do you remember the 1s orbital? It's kind of small. What about a 2s orbital? Go from 1s orbital to a 2s orbital. 2s orbital is bigger. And then the 3s orbital is bigger. And so the higher the n values, the bigger. And so what we're looking at here is this. Even though these are in the fourth shell, there's a difference in the position of these. So when we look at the n equals 4 orbitals, 4s and 4p, those are big, like this. If we look at these d orbitals, those are a lot smaller. So going from 3 to 4, it gets bigger. Okay, the energetics are a little bit different here because this is how we fill it. But if you're an oxidizer and you're going to attack germanium, germanium can lose up to 4 electrons. Which 4 would it lose? Would it lose these 4 p's first here? Well, an oxidizer comes in, oxidizes those. Yeah, it makes sense. You know, the 4 p's are out there. You know, the outermost electrons. The outermost electrons are the ones that are going to be oxidized if you're going to oxidize something. And so oxidizer comes in here and oxidizes those. Okay, that takes care of 2. But there's still potential to lose more. In fact, oxidizer comes in, takes these 2. Now, if the oxidizers were, if the oxidizer further attacks this, do we expect to lose the 3D or the 4s? I mean, which one gets attacked? And it turns out it's the 4s because of just the size and stuff. So it's a little bit weird. These 3D are considered core. Core electrons. Oh, those are considered core electrons because of the distance from the nucleus. So, even though they are in the fourth shell there. And so, let's see. So it's easier to see in terms of electron configuration. In terms of electron configuration, what we can do is rather than rewriting this all out, 1s2, 2s2, 2p6, 3s2, 3p6, what we can do is we'll just take the argon core, we'll say argon, and then we'll go 4s2, 3d10, 4p2. And so this is how they fill. So this is the fill order. So if we're putting in electrons, we're going to put in the next electron into the, where can we fit in some more electrons? The p, before p, because the max capacity of those are 6. But we also have another order. This would be the that's filled and losing order. The losing order is going to be like this. The electrons that are lost are going to be the furthest away nucleus. So that means it's going to go like this. 3d10 are going to be the closest to the nucleus, followed by the 4s2, followed by the 4p2. And so if you're an oxidizer, the first electrons you're going to see are the n equals 4, the 4p, and you'll oxidize those. The next electrons you'll see are the s, so you oxidize those. That doesn't happen here. And so what we'll do is we'll call this the core here, and then this will be the valence. And so even though it does look different, you know, when we compare germanium with silicon, it's the same, because take a look at the valence. The valence shell configuration is ns2 and p2. Leading to similar chemical properties. Now, when we add more shells of electrons, the size changes. It gets bigger and bigger as we go down. All right, so let's get a little bit of practice writing an electron configuration. Okay, can you write the electron configuration for arsenic? Here, AS. AS is 33 electrons. But actually, I wanted a little bit more. Can you do the energy level diagram and the electron configuration for arsenic? And then tell me what the core electrons are and the valence electrons are for arsenic.